Okay, so in the last lecture, we have seen this method, which is stability of earth den or stability of slope for the earth den. And we have seen these three conditions: stability of downstream slope during steady steepage, stability of upstream slope during sudden drawdown, and stability of upstream and downstream slope during immediately and after construction. After this method, I have shared one problem video, solved problem video, in which the stability of slope for earthen dam with Swedish slip circle method is been actually solved. Right now, let us move further. This is all we have discussed last time. Now, today we are going to discuss two methods. One is the friction circle method, and other is the Taylor stability number. This particular friction circle method is being used for three different conditions. First is it is used for total stress conditions. Second, it is used for cohesive friction soil, right? So this method is useful for this type of soil, right? And the circle, whatever you are going to draw, the friction circle you are going to draw, that is a concentric with the slip surface of the circle. In this method, also we are assuming the failure surface of the slope is an arc of the circle, or we are assuming it is a circular failure. Right? Okay. Now let us see this particular figure. You can see this, that this is a particular slope that we need to analyze. Now assume this is a circular failure or the slip circle through which the particular slope is going to be failed. In such conditions, you need to understand what are the different forces to be act on the slip circle, and through this particular method you are going to find out the factor of safety for the cohesive friction soil. Fine. Let's see what are the different forces which is being going to act. First force which is going to act on this particular sliding mass, which is first is the weight of this particular sliding mass, which will be acting downward. Second is there is a reaction force which has been acting from somewhere here, which is a reaction force which also act against this particular force, which is this on this upper side. And the third force which is going to act, which is the cohesion of the soil, which is probably a resisting force of this particular friction circle. Now to analyze this, let us come back to this particular slide, and then I will explain each and every component of this circle. So as friction circle method is assumed, the failure surface as an arc of the circle, whatever the figure we have shown is drawn with the radius r, and O is the center of rotation. Am I right? If the concentric circle is drawn with the point O as a radius of r sine phi, right, then this particular circle is known as friction circle. If I again go back to the figure, and you can see this is the one center through which I can actually draw this particular arc with the radius r, right? And from this center, same center, if I draw the circle with the radius of r sine phi, where phi is the angle of internal friction. So if you draw this circle, then this r sine phi circle is known as the friction circle, right? This r sine phi, again I'm repeating, is known as friction circle. Okay. Now let us see how this particular method is being analyzed. So what you need to do is, I will take, you can say one, I'm not going through the whole method line by line. I will just explain you here that how this particular method is being actually analyzed. For example, just imagine you need to solve this particular thing with help of one example. So let us draw one figure with the graph paper, that this is the particular slope that you need to analyze. So I'm drawing the same slope here that you need to analyze with some scale. So you can assume certain scale here. For example, if you take the scale is equal to 1 centimeter is equal to 2 meter, for example, okay? And with this scale, you have plotted this particular slope with this. Let's assume this is point A, this is point B, this is point C, and so on. Now, just imagine this is what your center of the sleep circle, right? And from this center, you are going to draw an arc which is having radius r. So for example, I am just, sorry, I think, let's see this. What I need to do is, I will join these two. So this is the one. This is the one which is having a radius r. Now from this center, you draw the circle as you have drawn in the case of previous one. So this is the circle that you have drawn. So this is your sliding surface. Okay. Now what you need to do is, first you need to draw this particular friction circle with a radius of r sine phi. So from here, you take the r, you know, sine phi you can calculate, and with this circle you can draw this particular circle which is having a radius of r sine phi. Right? Okay. Now what you need to do is, let's see. First you draw this, then you calculate this particular length. I'm joining point A and C, so which is like this. This angle, I'm supposed to say this angle is theta or delta, whatever you say. Let's say I'm putting, you can say the delta, because last time we have seen it is a delta angle. So I'm taking delta, whatever it is. From this delta angle, I'm bisecting this particular arc into the two components. So like this. So this is delta by 2, delta by 2. In this way. Now what you need to do is, first you need to find out the weight of this particular arc, that is A, B, C, A, right? How will you do this? Either you can adopt, you can say by any method, like for example, suppose I will take one more point here so that you will actually realize that what I need to do. For example, I'm taking one more point D here. So I'm saying that I need to find out the weight of A, B, C, D, C, D, A, right? Okay. So what I will do is, first I will take the area of this hole, like O, A, D, C. Am I right? I'm taking O, A, D, C minus area of this triangle, which is O, A, C. So I will get this component. And from this, if I minus again this, or if I plus this area of ABC, I will get the entire arc. Am I understood? Again, I'm repeating. First, what you need to take the area of this minus area of this triangle. So you will get this portion, but I need, you can say, the whole wedge. So what I will do is I will add this triangle ABC. How will you find out the area of this hole? If you want to calculate the area of this hole, then you will actually use pi r square, which is the area of circle, multiplied by 2 pi r delta upon 180. So that you will get, you can see the value of this whole, you can see the circle. Then you know the area of triangle, which is this ABC you want to, sorry, OAC you want to do. So it is 1/2 into this length, that is this length, O, and this is, let's say, E. Then I'm saying OE into AC, and then area of this, which is ABC, that is also you can take, that is this B, and this portion, whatever the perpendicular length, this is also you can calculate easily, right? So BC, and you can say this horizontal length. So if you do it, then you will get the value of W here. So you can get you can say the W is equal to some value in kilonewton, right? Now again you need to take the scale, and also you want to find out the CG of this. So W is acting at some point CG from this particular point. So suppose I'm finding out the CG, which is at distance D from this surface. This particular W force is acting in the downward direction. So from this, I will actually plot my value of W. I'm just showing only the direction right now, not the component. However, the value of W, that value is already you have found out with this. Now W you have said. So W I have plotted. Now your cohesion, which is going to act on the sleeve surface, which is along this particular line, So what I'm doing is, I am drawing a line which is parallel to this at some point here. So this and these two lines are the parallel. So this will be the component of C. And now at this point, I'm going to join a line which is tangential to your friction circle and which pass through this particular point. So this is your reaction R. So you will have this three triangle. One is C, which is a cohesion, which is acting in this direction. Then the W, and you will have the reaction R. Now, if you have this particular value, suppose you have calculated the value based on the analysis of this particular triangle, and you have arrived at some numerical value, then again you take some scale. Let's say suppose this value is, let's assume a 2000. Okay. I'm just assuming any random number that you have calculated from the analysis of, I'm again repeating, that you have calculated from this triangle minus this triangle minus plus this triangle. Okay. So you will arrive at this particular value. Now to plot this, again you need to take the sum scale. So suppose I am taking 1 centimeter is equal to, let's say, 500 kilonewton. Then for plotting this W, I need to plot this component of all these things. So what I need to do is, let's assume I need to take the plotter, and I will plot this W, which is in this direction, which is W, sorry, a vertical line I need. So this is, just assume this is a vertical line I'm drawing with the mouse. So this is W. Okay. How much it is? This is a 4 centimeter line. Okay. Then from this line, you need to draw the value of C. I do not know what is the length of C. So I'm plotting, you can say just a random number here, right? And then the reaction, which is parallel to this R line. So the reaction I'm going to draw from this line. So this will cut this particular line in this direction. So you will get the direction of C. So you can get this value, this length, multiplied by whatever the scale value, you will get the value of C here. And at the same time, you can get the value of R here, which is in this direction. Now, once you calculate the value of C here, this is a cohesion. And now you need to find out the value of factor of safety. The factor of safety is the C divided by Cm, where Cm is your mobilized cohesion. Now, how to find out the value of mobilized cohesion, which is written in the formula, which is nothing but it is the ratio of L arc by L bar. Now, what is L bar? L bar is nothing but this is L bar, this length. And L arc is this. right? So this will give you the value of Cm multiplied by some constant value. I will actually let you know what is a constant value here. So this will give you the value of Cm. If you put this value of C by Cm, then you will get the factor of safety for this slope. And this is what all about this particular friction circle method is, right? So this is what the story I have written here, that has been shown here. Whatever I have shown here, that has been explained here. Okay, so let's go one by one so that you will get to know that how this method is being plotted. So as I said, the forces acting on the sliding wedge ABDA, which is as per the figure, which is the weight W, total frictional resistance force, which is R, and the total cohesive resistance, that is CLR, which is developed on along the slip circle. If we divide the slip circle into the number of elementary arc, which is delta L, the elementary reaction delta R of each arc acting on obliquity phi to the normal of the arc will be tangential to the friction circle. We all already seen this thing, right? So the, yeah, I will answer you if in the last. The elementary reactions delta R at point E and E1 is tangential to the friction surface. I will show you how this is. And the point of G of intersection of EF and EF1 is slightly away from the circles. Now, what you need to do is total cohesive force Cm into L arc, which is to be assumed, okay, which is to be assumed to consisting of the elementary resistance, which is Cm delta L, and the arc AD is divided into the number of elementary arc. You can divide, or I can, as I have taken, you can say that as a whole circle. And you need to draw the force polygon, where L arc is the length of the chord, which is in my case I have shown here, right? Once you find out this particular value of this, you will get this particular entire relation, which is Cm into L into A. A is nothing but which is the length, which is this, and this value of A you can find out with help of radius into L arc upon L bar. That's I've shown here. I've shown this particular constant, which is this. Now, so as I said, this L arc upon this, so this is the value of A that you will get it from this. So if you put this value, then you will get the value of Cm, and based on the value of Cm here, they have written Cc. So this factor of safety against the cohesion is been calculated, and this is all about, you can see, the friction circle method. You can see this, whatever I have explained here, that is being shown here. I can take one or two questions if you have, and then I will go to the next method. Yeah, radius may be given to the radius may be given in the question, since you don't need to take number of trials. So radius can be given in the questions, right? I mean, to avoid the number of trials. Otherwise, you need to take number of trials. For exam point of view, the radius will be given, definitely. I will also post after this one more example video, which is based on the friction circle method, so that whatever I have explained to you, it is thoroughly clear. So I will post the video in the same way that I have posted for you can say Swedish slip circle method. So basically this particular method will be cleared down. Okay, I hope it is clear. Any other question? Okay, if not, then I will go further. Let's see. This is the Taylor stability number. Although we have talked this particular method in detail while we are actually learning the stability of infinite slope, and I think if you are remember this particular equation, you are familiar with. If you go to the stability of infinite slope, you will also find out such relations in that also, right? However, specifically the Taylor stability number, how it has been developed, it has been plotted here. The total cohesive force CL arc, which resists the slipping along the slip arc at critical equilibrium, is proportional to the cohesion and length h of the slope. I think it is but natural. The force causing instability is the weight of the wedge, which is equal to the unit weight and the area of the wedge. which is proportional to the square of the height. As such, it is the overburden. Hence, the weight of the wedge is proportional to gamma into h square. And if you take the factor of safety due to the cohesion, then this value will come C into H divided by FC into gamma H square. So C up this HH will go. So C upon FC into gamma H will give you the stability number. This equation we have already seen while we are discussing stability of infinite slope. Now, dimensionless quantity C upon FC gamma H, which is called as the Taylor stability number Sn. If I convert this particular equation in the mobilized form of cohesion, so once after the slope is going to be failed, at this condition, the cohesion of the slope will be converted to the mobilized cohesion. In such cases, the Cm is nothing but the C upon the factor of safety due to the cohesion. So, or you can take a factor of safety of cohesion in here, then it is nothing but C upon Cm, same equation. So this equation will be written as this. So whatever the value of Fsn, this is Sn is C upon Fc into gamma H, this equation is there. Now this is C upon Fc, we have already said it is a Cm. So this is Cm I'm replacing here upon gamma into H. So this value will come. Now if the Hc is the critical height, when I'm taking the critical height, it means the factor of safety I need to assume as a 1 because it is a critical conditions. So if I take the factor of safety due to the cohesion in terms of the critical height, then this value will come Hc upon H. So the stability number, the original equation, which is C upon Fc into gamma H, will be turned down to C upon, you can say, gamma into Hc, because I need to put, you can say, this value into this. You can say this H will go here and this value will convert to this. Again, I can convert this particular value by C upon gamma H by means of the previous equation, which is this. Okay. So these equations you can actually very well aware of. Using this friction circle method with an analytical procedures, whatever the method we have seen as a friction circle, this Taylor has stabilized the number Sn for number of trials. And he has assumed, and he has actually given the chart which gives the value of stability number for various value of phi and the slope angle I. I will show you this graph. So the table is also being given based upon this particular chart and for the cohesive soil, because since this particular method is being used for cohesive soil. So this particular table has been given. You can see for various value of phi is starting from 0 to 25 and I is this, and the Taylor stability number Sn has been plotted for all these two values. Here also you can see the value of Sn for the cohesive soils. Slope angle is 90 to 7.5. I hope all the is been considered, and also the depth factor is been considered. So that is based upon the critical height of the slope. This values has been calculated. So both the values has been given by the Taylor. Now what you need to do, it should be noted that the Taylor stability number is based on the factor of safety Fc with respect to cohesion. Assuming that the frictional resistance between fully mobilized means the factor of safety F of phi, which is with respect to the internal friction, which comes to the unity. The stability number does not include the friction terms because it is applicable for cohesive soil. When the soil possesses both cohesion and friction, the factor of safety F is being provided with respect to cohesion as well as for the friction. You need to calculate, separate it out. So average shear stress which could be developed with the given factor of safety F would be, S will be nothing but C plus sigma 10 phi, whatever the value you have seen, this value will be multiplied by the factor of safety. You will get this value. Now, if you calculate the value of Taylor's, if you go with the Taylor stability curve, then the effective value of phi, which is the mobilized one, you can calculate with the help of this equation. So whatever the value of internal friction divided by the factor of safety, and if you take the 10 inverse, then you will get the value of phi m, right? Now, for example, suppose if you have the value of phi is 18 degree, factor of safety, if you want to consider is a 1.5, then the phi m, which is nothing but the 18 degree, which is phi divided by the factor of safety, which is 1.5. So the 12 degree, which is value of phi m, which will become. And the value of Sn is, you need to take it from the value of corresponding value of phi m. So which is from here, right? So you will get the value of Taylor stability number. Now for the purely frictional soil, means the cohesion equal to 0, right? So cohesionless soil, sandy soil, the stability number is 0. You can see here from this curve also, you can actually visualize as this value goes down. You can say this value is 0. For C is equal to 0, here there is no plot for the C is equal to 0, because all the values varies with respect to phi. So if you have a value of C which is 0, in this case the Taylor stability number is assumed to be a 0. The stability of slope then the entirely depends upon the slope angle. So basically in that case, if the Taylor stability number for C is equal to 0 is 0, then it is depends upon only the I. In this case, the factor of safety with respect to shear strength that you can calculate with respect to this formula. In this case, the factor of safety with respect to cohesion as well as with respect to internal friction, which is equals to 0, right? So in order to determine the value of F, you need to use several trials. So this trials has been plotted. You can see this particular graph where the slope angle has been there, value of various phi is also been plotted, and the stability number has been plotted, and you can find out the value of various value. Whatever we have seen in the table, the same table has been converted into the chart. So either the table will be given, either the chart will be given if you have some problem in the relation to Taylor stability number, right? To start with this, so phi m you can calculate as we have seen this particular equation. Now from the table, you can find out the value of Sn with corresponding value of phi m. Then with this value of Sn, once you know the Sn, you have the gamma, H and C, you can calculate the value of Fc. So for each value of F phi, once you once you assume the value of phi, so this is phi F phi, that is first trial. Based upon that, you will get the value of phi m. Based upon that, you will get the value of Fc. From phi m, you will get value of Sn. Sn from this value, you will get Fc. So for one value of F phi, you will get one value of Fc. Similarly, you can take the number of trials and you can plot this particular curve between Fc and F phi. You will get this particular curve, right? So this way, you can actually calculate the value of factor of safety in this case. As I said, for the cohesion, purely cohesionless soil, this all the values is equal, so that the chart is actually bifurcating from this particular point. So this is the Taylor stability number you can actually calculate, right? Such trials you need to take, and you need to find out the factor of safety, right? Corresponding to each trials. You can find out the long-term stability as well as the stability of submerged slope, as we have taken in the case of previously, that if you want to calculate the submerged slope, you need to take the value of gamma, which is equals to the submerged density, right? Similarly, the weighted frictional angle, which is corresponding to phi with respect to the water, you need to take, and which will be compute the value of Sn. This is what just a small addition. Very important for this method is this table, this equations, probably this equations, this particular concept, I think, and based upon how to develop this particular thing, how to develop this particular chart, right? So this is all about, you can see the stability number. So this way you can actually find out the stability of any slope with help of you can say stability number, right? If you have any questions, I can share it. Yeah, I mean, Rabens and Kalman theory, I will try to find it out, and I will actually post if I get it. Okay. Otherwise, I need to solve it by my hand. But one more questions I need to now take it up with your opinion that now this chapter is over. I need to cover one more chapter, which is a bearing capacity. Now, as per the conversation with Dr. Manas Bhoi, he would like to take this particular chapter. What would you like? I mean, so whether the Manas Bhoi is okay with you, and if he takes the lecture, you can say the further for the bearing capacity. Then I will stop here. My syllabus is actually getting over. I need an answer from you people. Okay. Okay. So Manas sir is also going to take, I will also take. Okay. So whatever you feel like, I mean, but I will take very concisely. Manas boy will take in detail. Okay. So I will try to take it one. Okay. Fine. So from tomorrow onwards, we will start with the bearing capacity chapter, right? Please join us. And I will also post, you can say, this video as well as the bearing capacity PPT to you, right? Before I will start my lecture tomorrow. Thank you very much for joining. Thank you very much.